Okay, let's talk about the next generation of flight. Advanced Air Mobility, or AAM.
Right.
For the better part of a decade, this industry has been, swimming in the conceptual phase, beautiful prototypes, stunning renders, and this promise of air taxis.
Absolutely.
But now we are witnessing a crucial transition. The shift is moving from that fun blue sky world of prototypes to the intensely serious, non-negotiable world of airworthiness certification and commercial operation.
Exactly. And that pivot point is where, engineering rigor really meets reality.
Okay.
When you move from just demonstrating a capability to proving airworthiness, every single subsystem on that aircraft is placed under a microscope.
Right.
And what we find when we analyze the entire system is that all the incredible technology, all the massive investment, it all hinges on one single non-negotiable variable,
Which is?
the safety of the powertrain.
And this is precisely where we encounter what the industry, I guess, refers to as the valley of despair. This is the core structural challenge facing the purest all-electric eVTOLs right now.
It is.
The reality is that current battery technology, when you measure it at the system level, with cooling, housing, and protection, is only reliably delivering energy density in the range of about 150 to 170 watt-hours per kilogram.
And that number, 170 watt-gram, is simply insufficient to meet commercial mission demands.
Just not enough.
Not even close. If you look at this through the lens of an aerospace architect, you realize that bottleneck means you cannot simultaneously satisfy two critical requirements.
Okay, what are they?
First, the long-range mission profiles you need for economic viability, say regional travel of 100 to 150 nautical miles.
Right.
And second, the incredibly demanding regulatory reserve energy requirements.
That's the real killer, isn't it? It's not just about getting to the destination. It's about having enough gas in the tank or charge in the battery to deal with the unexpected.
Precisely. If a typical mission requires 100 nautical miles, the regulations mandate significant reserves. You might need enough energy to fly another 20 miles to an alternate airport. Or, crucially for a VTOL, enough power to hover for another 30 minutes in congested airspace while you wait for an ATC clearance or resolve a ground issue.
So that reserve eats your payload or your range.
It eats your range. If you lift off with 4 passengers and your available energy density is only 170 WHQLI, you quickly realize you might lose 20 or even 30 miles of potential range just meeting that regulatory reserve.
Wow.
And that forces manufacturers to dump the mission profile, which severely limits the economic feasibility.
So if pure electric hits this regulatory and physical wall in the regional space, the solution we are diving into today is the P13 series parallel hybrid propulsion system.
That's it.
This isn't just a technical choice. It sounds like the definition of a strategic architectural compromise designed to bypass this valley of despair.
It absolutely is. Speaking from the perspective of an aerospace architect, the P13 approach is a foundational shift. It's about, an engineered compromise that leads to operational superiority and, more importantly, certifiable safety.
How so?
It elegantly combines the power density and efficiency advantages of thermal power. That's your internal combustion engine or maybe a microturbine for that high-efficiency, long-distance cruise.
Okay.
With the environmental and low-latency advantages of pure electric for low noise, zero emissions during the critical city approach, takeoff, and landing phases. It is fundamentally an architecture designed to jump that energy density wall completely while maximizing safety assurance.
So our mission today is to understand how this highly complex integrated system, the P13, proves what we're calling architecture-driven safety. Because when you fuse thermal, mechanical, and high-voltage electric systems, the complexity just skyrockets. We need to know how the very structure and design of the machine can guarantee compliance with the most rigorous global airworthiness standards.
And we have to start by being crystal clear on what those standards are because they dictate every single engineering choice we make. The ultimate safety target is non-negotiable in modern civil aviation.
And that target is?
The probability of a catastrophic failure must be less than 10 to the minus 9 per flight hour.
That number 1 in a billion is just staggering. Can you put that in perspective for the listener?
Sure. It means that if you operated this vehicle continuously, 24 hours a day, 365 days a year, you could expect one catastrophic event on average every 114,000 years.
Wow.
This isn't a suggestion, it is the legal requirement. And critically, this is the same exact safety standard required of large transport category jets like the Airbus A320 or the Boeing 737.
So when an eVTOL shares the sky with established commercial traffic, it has to meet the same burden of proof.
It must. And that's why the foundational principle driving all our work from the earliest conceptual sketch to the final wiring diagram is that safety must be designed in based on top-down, systematic planning, not merely tested in afterwards.
Okay, let's unpack this monumental 10 to the minus 9 goal. If I'm a manufacturer investing billions, I can't just assert I'm safe. I have to build a legal, quantitative, and auditable case. Where does this requirement come from, and what is the international framework used to prove it?
This is where we apply the MECE principle, mutually exclusive, collectively exhaustive to our regulatory scope.
Okay.
The need for a cohesive airworthiness certification basis is the strategic first step. If we only comply with, say, the FAA, we restrict ourselves immediately to the U.S. market.
So you have to think globally from day one.
You must. We have to align with the three main regulatory bodies from the very beginning to ensure genuine global market access and future compatibility.
Let's start with the European Union Aviation Safety Agency, EASA, which, often acts as the global safety benchmark.
Absolutely. EOS mandates compliance with SC VTOL 01 Issue 2, and specifically the enhanced category.
Okay, what do those mean?
So SC VTOL is the special condition for VTOL aircraft, which is essentially the new rule book for this class of vehicle. The enhanced category is the highest bar, and it's applied when the aircraft flies over congested urban areas.
Which is the whole point of most of these vehicles.
Exactly.
So what are the primary demands of this enhanced category?
It dictates two core safety principles that fundamentally structure our entire design. First is the no single failure, or NSF principle.
Single failure.
It means we must prove that the failure of any single electronic, mechanical, or software component, no matter how small, must not lead to catastrophic consequences. This is what drives our deep need for redundancy.
And the second principle?
Second, of course, is that quantitative 10 to the minus 9 probability target. The NSF principle is the qualitative filter, and 10 to the minus 9 is the quantitative proof. That combination becomes the highest guiding principle for the entire P13 architecture.
And across the Atlantic, how does the Federal Aviation Administration, the FAA and the USA, approach certifying this revolutionary vehicle class?
For the FAA, the certification pathway uses the 14 CFR 21.16b special class for type certification.
Why special class?
Well, because eVTOLs are a new powered lift category. They don't fit perfectly into the existing small aircraft rules, Part 23, or transport aircraft, Part 25.
I see.
The special class lets the FAA tailor the requirements. The specific technical path, what we call our means of compliance, or MOC, involves referencing ASTM F3230-21A, which is the standard for small aircraft safety assessment.
Good.
And that standard provides the structured methodology for conducting hazard assessments and fault analyses, helping us satisfy core airworthiness requirements like those under Section 23.2510.
And notice the source material also mentions the Civil Aviation Administration of China, the CAAC, which is increasingly crucial for global manufacturing and operation.
Yes. The CAAC has their own evolving regulations for a powered lift aircraft, and for a highly integrated, complex hybrid system like the P13, the CAAC review process places intensive scrutiny on specific clauses.
Like what?
Specifically on things like distributed power synchronization and software autonomy.
What does that mean in practice?
Well, because the P13 has an ICE and a generator, plus a battery, all feeding power to a common high-voltage bus, the CAAC needs extra assurance that the system remains stable, synchronized, and reliable.
Even with all those different sources.
Right, especially with decentralized power sources operating under a complex autonomous control architecture. This requires extensive evidence demonstrating transient stability and very robust fault isolation.
So once we have this stack of legal requirements, EASA, FAA, CAAC, we need the actual engineering methodology. You call this the aerospace dual pillars. This is the systematic approach that transforms those goals into a repeatable, auditable engineering practice, right?
Precisely. This is the application of the SAE Society of Automotive Engineers standards that define how we build airworthy systems. They are the two essential pillars of aerospace system safety.
Pillar 1, ARP 4754A. You refer to this as the architect's blueprint. What makes this document so fundamental?
ARP 4754A mandates the rigorous V-model development cycle.
The V-model.
Think of it as a comprehensive map. The left side of the V is decomposition. You take the highest level requirement, say the aircraft must fly, and you trace it downward, systematically breaking it into aircraft functions, system requirements, item requirements, all the way down to the component software code or a specific hardware circuit.
It ensures absolute traceability.
Absolute. If a regulator asks, why is this line of code here, we can trace it all the way back up to a fundamental aircraft function that's necessary for safe flight.
And here's the key strategic insight for eVTOLs,
Yeah.
right? The propulsion system and the flight control system are deeply, and I mean inextricably, integrated.
This integration is the challenge that elevates the P-13's required integrity. In a traditional plane, the engine provides thrust, and wings or the rudder provide control. They're separate.
But not here.
In an eVTOL, differential thrust, just varying the speed of the propellers, is the primary flight control input for yaw and often for roll.
So if your motor fails, your flight control has failed.
Exactly. If your propeller pitch or your motor torque fails, the entire flight control surface has essentially failed at the same time. Therefore, that top-down integrity defined by ARP 4754A is an absolute prerequisite for certifiable safety. You have to prove the safety and reliability of the engine before you can even certify the basic controllability of the aircraft.
Which leads us to Pillar 2, ARP 4761, the structural engineer's proof. This is where the paper analysis stops and the actual quantitative mathematical proof begins.
ARP 4761 provides the analytical toolset to satisfy that 10 to the minus 9 number. We start with the functional hazard assessment, FHA, to systematically identify every possible way the system could fail and what the consequence would be.
And
Then we deploy the analytical heavy hitters. We use fault tree analysis, FTA, for deductive failure probability calculation.
can you give us a quick concrete example of how an FTA works in this context?
Certainly. The top event of the fault tree is the catastrophic outcome we want to prevent, like total loss of thrust or TLOT. We work backward. What causes TLOT? Well, one major branch is loss of high voltage bus power.
Right.
And what causes that? It splits into mutually exclusive paths. Battery contactor failure, or P1 generator failure, or major HV bus short circuit, and inability to switch to a redundant path. Each of those branches is then broken down even further to component failure rates, like the probability of a specific transistor failing.
And you add it all up.
You sum those probabilities, and you prove mathematically that the probability of that top event, TLOT, is less than 1 in a billion.
That deductive approach is then complemented by an inductive approach, the FMEA.
Yes, the failure mode and effects analysis, or FMEA works forward. We take every single component, say a specific inverter capacitor, and we ask, what are its known failure modes? Short circuit, open circuit, leakage.
And then you trace the consequences.
We trace forward to see what effect that local failure has on the rest of the system. FTA and FMEA have to cross-check each other, ensuring every single failure is accounted for, deductively and inductively. That's what creates a truly comprehensive and auditable safety case.
Now that we know the rules of the game, the 10 to the minus 9 target and the dual engineering pillars, let's look at the engine itself. The philosophy is safety is designed in. How does the P-13 architecture inherently provide this safety layer physically?
Following that MAC principle, we first have to define the system's safety boundary very clearly. As an architect, you can't certify what you don't analyze completely.
So what's in the box?
For the P-13, this boundary is comprehensive. It includes all components involved in generating, converting, or controlling the thrust.
Walk us through the components within that boundary.
We define 3 internal domains. First, the energy sources, the high-voltage battery system, or ESS, and the physical fuel system. Second, the conversion elements. This includes the internal combustion engine, the ICE, the P1 integrated starter generator, the main P3 propulsion motor, and the really critical mode-switching component, the K0 decoupling clutch.
That clutch sounds important.
The K0 clutch is the physical core of the hybrid functionality.
And the third domain.
Third, the control and distribution elements. The inverters that manage the electric current, the power distribution unit, or PDU, and the vehicle control unit, the VCU, which is the system brain that arbitrates energy flows and thrust commands.
So every single one of those components is part of that 1 in a billion calculation.
Every single one, and subject to the highest levels of design rigor.
The genius of the P-13 architecture as a safety feature seems to lie in its multimodal paths. It's not just redundancy. It's independent redundancy based on 2 physically distinct energy paths.
That structural independence is the physical foundation of our entire safety case. We have 2 main highly independent energy paths, thermal, which is fuel, and electric, which is the battery, and they combine to allow for 3 core operational modes.
Let's start with Mo A, the efficient cruise power.
Mode A is the thermoelectric path. This is the primary cruise path designed to optimize fuel efficiency for regional travel.
How does the power flow?
Fuel goes to the ICE, which turns the P1 generator. The electricity that's generated is conditioned and delivered to the high-voltage bus, which then powers the P3 motor to turn the propeller.
So even with the engine running, it's still an electric motor driving the prop.
That's a key point. Even though the ICE provides the primary energy, the thrust output is still digitally controlled by that electric P3 motor, which means we maintain precise digital control over the thrust.
And Mode B, the pure electric path that you'd need for dense urban environments.
Mode B is the pure electric path. This is the immediate low-latency path. Battery power goes directly to the HV bus and then to the P3 motor.
When would you use that?
We reserve this for vertical takeoffs, landings, hovering maneuvers, and those fast response flight phases where immediate torque response is absolutely essential. It's also the primary backup path should the ICE or the P1 generator fail during cruise.
And Mode C, the mechanical lifeline. This seems like the ultimate physical contingency plan.
Mode C is the mechanical direct drive path. In specific controlled conditions, primarily during cruise, the ICE can bypass the entire electrical system, the P1 generator, the HV bus, all the inverters, by engaging that K0 decoupling clutch.
This directed drive.
It is. Fuel goes to the ICE, the K0 clutch closes, and the ICE directly drives the propeller shaft. It is specifically engineered as a mechanically separated, redundant backup path designed to provide enough sustained power for continued safe flight and landing, or CSFL, even if the entire electrical generation system fails.
That clutch is clearly the central nervous system of the whole redundancy plan. But if Mode C engages, you have to ensure the mechanical system operates without the fine-tuning of the electric system.
That is the critical challenge, and it's why the clutch itself is subject to the highest design assurance levels. If Mode C engages, the system has to ensure the ICE output speed is synchronized precisely with the existing propeller speed.
To avoid a huge mechanical shock.
Exactly. To prevent shock or propeller overspeeding, which could cause a catastrophic structural failure worse than the original problem. The timing of that K0 clutch engagement, which is managed by the VCU, has to be in the order of tens of milliseconds.
That's incredibly fast.
It has to be, to keep the synchronization accuracy within a very tight band, typically plus or minus 2% RPM.
So the core safety thesis emerges from this triple mode design.
The core safety argument is the high degree of independence. If we apply that no single failure principle, we have to demonstrate that if any single component fails, say a catastrophic failure of the ICE or a total disconnect of the main battery contactor, the remaining independent modes must provide sufficient power for continued safe flight and landing.
So the system has to be smart enough to recover on its own.
It has to identify the fault, isolate the failed path, say, by opening the K0 clutch or cutting the PDU output, and seamlessly transition the load to the remaining path. That physical and logical ability to switch, isolate, and recover is the quantitative baseline for meeting that 10 to the minus 9 standard.
We have to systematically identify every way this complex machine can fail, from the smallest wire to the biggest engine component. This is where the functional hazard assessment, the FHA, comes in. This is the essential step in translating abstract risk into specific, hard-coded engineering constraints.
That's correct. It's the structured, top-down way to think about failure. We start with the top-level aircraft functions, or TLAFs, that are absolutely critical to flight safety, and we adhere to the structure provided by ASTM F3230.
And for the P13 powertrain, what are those three top-level functions?
We define three main areas of safety responsibility. TLAF-01, provide controllable thrust.
That seems obvious.
It's obvious but complex. It includes thrust magnitude, directionality, and the latency of the response. Then TLAF-02, manage energy storage integrity. This is critical, covering the safe containment of both the high-voltage battery and the fuel systems.
And the third?
TLAF-03, prevent fire and high-energy release. This directly addresses the catastrophic risks associated with thermal runaway, high-voltage arcing, or mechanical rupture.
The FHA then maps these functions to specific failure conditions. We establish that the catastrophic classification demands a probability of less than 10 to the minus 9 per flight hour. What are the specific power system failures that fall into this highest tier of risk?
The primary propulsion system catastrophic conditions are total loss of thrust, TLOT, and asymmetric thrust.
Okay, TLT is clear. The aircraft can't fly.
Right. But asymmetric thrust in an eVTOL is equally devastating. Since differential thrust is used for flight control, an uncontrolled surge or loss of thrust on one side of the airframe creates an immediate, severe, uncommanded yaw and roll moment.
Loss of control.
For certification purposes, if that leads to loss of control within milliseconds, it is functionally equivalent to TLOT, and it requires that same 10 to the minus 9 protection level.
And the high voltage side has its own catastrophic risk.
Absolutely. The second major catastrophic risk is thermal runaway propagation within the battery system, leading to an uncontrollable, unextinguishable fire. Given the high energy stored in the pack, a thermal event must be prevented from spreading, because if it reaches a runaway state, the aircraft is essentially lost.
Moving down the severity scale, what are the hazardous failures? Those require the target of less than 10 to the minus 7 per flight hour 1 in 10 million hours.
Hazardous failures are severe, but not necessarily immediately fatal. They could lead to serious injury or damage, but the flight may be concluded safely, albeit with a lot of difficulty.
Can you give some examples?
Sure. One is being unable to disconnect high voltage after an incident, like a ground collision. If the main contactors weld shut, first responders or maintenance crews face an immediate, potentially fatal high voltage exposure.
I see.
Another key hazardous condition is the non-commanded K0 clutch actuation, the clutch engaging or disengaging unexpectedly. While this won't cause immediate TLOT if the other mode is ready, it could damage the P3 motor, severely compromise propulsion, and require an emergency landing.
This FHA then directly informs the Development Assurance Level Allocation, or DAL. You mentioned that this is where safety requirements stop being theoretical and start determining budget, timeline, and engineering effort.
That is the strategic significance of DAL. It converts the severity of a failure into the required rigor of development, verification, and testing. DALA is the most rigorous, and it dictates specific processes for both software under DO 178C and hardware under DO 254.
Let's nail down the critical DLA functions for the P13.
The catastrophic functions must be DLA. This includes the logic for total thrust control, FUNC-01, which encompasses all the VCU logic that arbitrates between the hybrid modes, manages synchronization, and commands the final P3 motor output.
And the battery.
And the battery thermal management system logic, FUNC-03, which monitors and controls the health of the battery to prevent that thermal runaway propagation.
You mentioned DALA, rigorous extreme. What does that actually mean for software development?
It is the Everest of coding standards. DALA requires 100% modified condition decision coverage, or MCDC.
And that's more than just testing every line of code.
Oh, far beyond. It means that for every logical decision within the critical code, like if temperature is high and current is high, then reduce power, we must mathematically prove and test every single combination of true and false outcomes.
That sounds incredibly intensive.
We are talking about testing millions of logical paths to guarantee no unexpected behavior lurks in the code under any combination of inputs. This effort dramatically increases the cost, time, and complexity, but it is the non-negotiable proof point for that 10 to the minus 9 reliability.
And the lower levels, DAL, B, and C.
DALB is assigned to the hazardous functions. K0 clutch control, FUNC-02, and the high voltage interlock loop, or HVIL, FUNC-05. These still require significant rigor, but less intense formal proof than DLA. And finally, DLC, major, is assigned to functions like P1 generation control, FUNC-04. A failure here might mean you lose the efficient thermoelectric mode A, forcing you entirely onto the battery.
So it shortens your range, but it doesn't crash the aircraft.
Exactly. It shortens your range, it may delay your mission, but the aircraft remains controllable and safe. This distinction between DALA, B, and C is what drives the entire engineering architecture. With the development assurance levels formally set, we move from the quantitative assessment to the technical heart of the system, the specific design choices made to eliminate the risks we've identified. To achieve DLA in an integrated system like P13 requires moving beyond simple duplication.
Right.
We have to implement 3 core strategic safety principles.
Strategy 1.
Right.
Dissimilar redundancy, which is your engineering defense against the existential threat of common cause failure, or CCF.
CCF is the hidden enemy in complex systems. If you just duplicate everything, using 2 identical controllers, running the same software, powered by the same power supply, and a lightning strike or a subtle software bug takes down one, it will take down both.
And your redundancy is instantly worthless.
Completely worthless. So to eliminate that CCF risk, critical DLA computing units like the VCU thrust arbitration logic must use heterogeneous processors.
So we're talking about mixing and matching different manufacturers, like an Intel and an AMD chip.
Exactly that kind of idea. You might use one controller based on an NXP chip series and the monitor on a completely different TI chip series. And crucially, they must run heterogeneous software architectures, often developed by different teams using different compilers or even different operating systems.
Why so much separation?
It ensures that a flaw inherent to one vendor's chip architecture or one compiler's output binary code cannot simultaneously affect the redundant counterpart. That difference provides the necessary independence for DLA compliance.
And this leads directly to the common architecture, the Digital Guardian.
This is the system's ultimate safety structure. The command-com path calculates the real-time thrust output. Running in parallel is the monitor, MON path, using that heterogeneous hardware and entirely independent validation software.
So the MON is checking the comms math.
It's doing more than that. It doesn't just check the arithmetic. It independently calculates whether the comms output command is reasonable and safe based on the current flight envelope and inputs.
Okay.
If the calculation results from COM and MON to diverge beyond a tiny predefined threshold, if the COM is having a digital breakdown, the MON has the highest authority, or veto power.
It can take over.
It can directly trigger a safe state by issuing an override command to the power distribution unit to cut the output. And this digital structure is reinforced by a physical layer. The MON and COM must be backed by dual independent 28V power supplies, so a single power bus failure can't compromise the safety net.
Strategy 2, deterministic failure mitigation. It sounds almost counterintuitive in a fly-by-wire aircraft, but for these high-energy, high-risk failures, you are relying on physical, predictable measures, not software probability.
When you're dealing with events like thermal runaway or high-voltage arcing, the reaction time you need is in the millisecond range. Software is too slow, too complex, and too probabilistic.
So you need hardware.
You rely on physical isolation and hardening. This means mandated physical thermal barriers and directional venting channels built directly into the battery packs to prevent cell-to-cell propagation. And for catastrophic electrical faults, we deploy hardware pyrotechnic fuses on high-voltage lines.
The pyrotechnic fuse, that sounds intense.
It is, and it's a vital safety component. Think of it as an explosive circuit breaker.
Wow.
When a fault is detected, like a dead short, the fuse uses a small contained explosive charge to achieve millisecond fault isolation. It physically vaporizes the conductor much faster than any standard mechanical contactor can open.
And that speed is critical.
It's critical for isolating a massive fault before it damages upstream equipment or starts a fire. We also use the high voltage interlock loop, HVIL, a low voltage circuit that, if broken, triggers a physical disconnect of the main high voltage power within 10 to 50 milliseconds.
Strategy 3, fail-safe design. This is the classic, elegant principle ensuring the system defaults to survivability.
Every critical actuator must default to a known safe state if it loses its control signal or power. The prime example in P13 is the K0 decoupling clutch.
How does that work?
It uses a normally open electromagnetic design. If the VCU fails, or the control line is damaged or loses power, the clutch automatically de-energizes and disengages.
It's the system's physical panic button.
It is. If the ICE suffers a catastrophic mechanical failure, a seized turbocharger, a broken crankshaft, that fail-safe design ensures the clutch separates automatically, preventing the massive mechanical failure of the ICE from physically dragging, damaging, or overloading the P3 electric motor.
Digging into the silicon now.
Yeah.
To meet DAL, what does that mean for the actual components of the structure, the software?
On the hardware, DO254 DALA side, the core microcontrollers in the VCU and BMS have to be specific, safety-certified chips, like the TI Hercules TMS 570 series, that use multi-core lockstep technology.
So they're not standard processors.
Not at all. They run two identical computing cores in parallel, executing the exact same instruction at the same time, and they use integrated hardware-level comparators to instantaneously detect if the two cores produce even a single differing bit of data.
So it's constantly self-checking.
Continuous hardware-level self-checking for instantaneous error detection.
And for software, DO178C DLAA, you mentioned the need to create airtight compartments within the code.
That's time-space partitioning. We use safety-certified real-time operating systems, often ARIN 653 compliant, to isolate the critical control logic, the DAL stuff, in its own dedicated, guaranteed time and memory space.
It's completely walled off.
Completely walled off from lower-level, non-safety critical software, like data logging or non-essential diagnostics, which might be DALC. The fundamental guarantee is that a bug or a crash in a low-level logging function cannot possibly affect the critical thrust control algorithms.
The need for safety filters down to even the smallest purchased component. Give us specific examples of how sensor selection has to contribute to the safety case.
Look at redundancy requirements. For throttle position, we don't use single potentiometers. We use non-contact RVDT or dual Hall sensors. These feature cross-check capabilities to detect common mode voltage drift.
Okay.
Even more critical is current sensing, which is essential for overcurrent protection. We achieve redundancy there using dissimilar physics, pairing a shunt resistor sensor with a flux gate sensor.
Why different types?
If the readings don't match, we know we have a measurement error, not a genuine electrical fault. It prevents a simple failure mode in a measurement device from causing a system shutdown.
And for the actuators, like the high voltage contactors, they have to prove that they physically responded to the command.
Exactly. Critical actuators, like the K0 clutch or the HV contactors, must have independent auxiliary contacts. These are small, separate electrical switches that provide physical electrical feedback of the main contact status. If the VCU commands the contactor to open, but the auxiliary contact says, "I am still closed," the system immediately detects contact welding or mechanical jamming, isolates the fault, and reconfigures the power path. Functional safety goes far beyond microchips and code. The integration of mechanical, thermal, and electrical systems is equally crucial for preventing catastrophic single-point failures that originate in the physical world. This is all about containment and separation.
Let's start with mechanical and physical isolation. When you marry a high-energy battery and a fuel-burning engine, fire is, well, the highest consequence risk.
It absolutely is. The ICE and the P1 generator areas are explicitly defined as fire zones. These must be completely separated from the battery compartment, the cabin, and the avionics, using firewalls constructed from materials like ISO 2685 certified titanium.
That's a big weight penalty.
A significant penalty, but it's non-negotiable. Furthermore, any wire harness, fluid line, or control cable that crosses that firewall must use specialized fire-rated connectors and pass-through seals to maintain that isolation integrity for a defined period, like 15 minutes of fire exposure.
And the high-speed rotating components, the motors, the turbocharger, present the risk of structural breakup, a rotor burst.
This falls under EASA SCE 19 requirements for rotor burst containment. The housings of the P1 and P3 motors and the ICE turbocharger must be structurally designed to contain high-energy fragments from a rotor burst should a disc or blade fail at full speed.
And if full containment is impossible.
If it's impossible due to weight or mechanical constraints, we must perform a detailed zonal analysis. This analysis uses trajectory calculations to prove that the fragment path will not impact and damage any other critical systems like the flight control computers, high-voltage harnesses, or the battery packs. We literally map out where shrapnel would go.
Moving to electrical integrity, how do you ensure the critical thrust commands travel reliably across the bus, especially when dealing with such a complex hybrid system?
Data link integrity is paramount for controllability. Critical thrust commands can't be subject to network jitter or collisions. We have to use highly deterministic, isolated data buses that guarantee bandwidth and latency.
What kind?
Things like ARNC 664, AFBX, or T-Tethernet, SAE AS6802. These protocols prevent non-safety critical traffic like maintenance data or passenger Wi-Fi from causing packet delays that could result in thrust jitter or instability.
Which we've established is a catastrophic risk.
It is. Furthermore, critical sensor inputs like motor speed or bus current must use triple independent hardware interfaces to ensure redundancy not just in the data but in the physical connection itself.
There's also the unique challenge of operating at altitude, where the laws of physics change slightly regarding electrical conduction.
That's the challenge of Paschen's law compensation. Paschen's law describes how the breakdown voltage of a gas changes with pressure. At typical eVTOL operating altitudes, say 10,000 to 30,000 feet, the low atmospheric pressure dramatically lowers the dielectric strength of the air.
The air becomes a worse insulator.
A much poorer insulator. So to prevent corona discharge, high voltage arcing, or flashover on the 800-volt bus, our electrical clearance requirements have to be increased by 3 to 4 times over what you would use at sea level. We're structurally redesigning components just to make the physical gaps wide enough.
And the system needs to continuously monitor its own electrical health, even in flight.
That's the Insulation Monitoring Device, or IMD. It's a sophisticated safety feature that uses active pulse injection on the 800V DC bus to continuously measure the insulation resistance between the HV lines and the airframe chassis.
What happens if it detects a problem?
If resistance drops below a certain threshold, An alert is triggered. But crucially, the system is designed for maximum operational continuity. We maintain power. The system enters a safe limp home state unless the insulation resistance drops below a critical threshold.
So only then do you have to land immediately.
Only at that absolute low point, which indicates a near certain electrical arc or short, are we mandated to execute an immediate controlled landing procedure. We prioritize maintaining power over immediate disconnection unless the risk is absolute.
Finally, thermal safety integration. We keep coming back to the battery because of the potential for runaways. What are the specific requirements for containing that heat and gas?
The requirements are incredibly strict, based on standards like DO311A. First, the battery pack design must include dedicated thermal runaway venting interfaces that lead to a safe exhaust duct outside the aircraft.
And you have to be careful where that vent points.
The design must strictly prohibit pointing the exhaust near engine intakes, propeller planes, or critical flight surfaces. These gases are high temperature, toxic, and conductive. We cannot risk a secondary fire or performance loss from the venting gas itself.
And the core containment requirement.
The design has to prove that a single cell experiencing thermal runaway must be contained within the battery enclosure for a minimum of 15 minutes without propagation to the next cell or an adjacent package.
And that 15 minutes is the critical window.
It's vital. It gives the pilot or the autonomous system critical time to recognize the threat and execute an emergency landing procedure. And of course, the design must ensure toxic gases do not vent into the passenger cabin.
Design is the foundation, but verification and validation V&V are the final essential proof. This is the right side of the V model, where we move from paper specifications to physical testing, and crucially, actively injecting failures to test robustness.
Correct. The 10 to the minus 9 proof relies on accumulating significant certification credit through a layered, integrated testing strategy. This hierarchy moves from the abstract to the concrete.
How does that hierarchy break down?
We start with hardware-in-the-loop, HIL simulation. This is where the real VCU software is tested against a digital twin of the entire aircraft dynamics.
Then you add real hardware.
Then we move to the Copperbird, which is a full-scale electrical bench test. It has all the high-voltage harnesses, inverters, and PDUs, but without the heavy engine or propellers.
And finally, the Ironbird.
The Ironbird, which is the full-scale mechanical and electrical system bench with the actual ICE, generator, clutch, and motors installed. This lets us test mechanical interfaces and real-world thermal performance.
Let's detail the specific failure scenarios you subject the P-13 system to, the fault injection testing, or FIT. This is where you deliberately try to break the machine.
We run hundreds of intentional fault injection tests. FIT-01 involves communication faults. We deliberately inject bus disconnects, data packet loss, and error frames into the control buses. This verifies the VCU can accurately identify the issue, isolate the unreliable data source, and seamlessly enter a safe limp home mode.
And FIT-02 addresses sensor integrity, where you rely on those dissimilar sensors.
FIT-02 simulates sensor drift. We use signal generators to simulate slow numerical drift or an instantaneous failure in critical sensors like throttle position or bus current. This rigorously verifies that our heterogeneous common comparators, the NXP chip checking the TI chip, immediately trigger protection mechanisms and override the bad data before it leads to an unsafe thrust command.
What about physical failures in the critical mechanical components, like the K0 clutch?
FIT-03 focuses on actuator failures. We simulate complex failures like the K0 clutch, mechanically jamming, or giving inconsistent feedback signals from its auxiliary contacts. We verify that the energy management system quickly detects the discrepancy, for example, VCU commanded open, but the feedback still says closed, and isolates the fault, potentially moving instantly from mode C to pure electric mode B to maintain safe flight.
You also need to revalidate the common mode analysis physically, right? You can't just assume the dissimilar systems won't fail together.
CMA validation ensures our CCF defenses hold up under real-world environmental stress. This involves simulating extreme environmental threats, like powerful electromagnetic interference or lightning strikes, on the entire vehicle structure.
To see if they both fail.
Exactly. We ensure the power supplies don't fail simultaneously or that the VCU shielding doesn't collapse. And critically, we use the Ironbird to achieve and demonstrate 100% MCDC coverage for all DALA software during testing to mathematically guarantee there is no dead code or unexpected behavior under any combination of input conditions.
The ultimate test short of first flight is the Ironbird, the full-scale system integration test. What are the key milestones you achieve there?
The Ironbird is where we accumulate huge blocks of endurance and stress certification credit. For instance, we execute mode switching endurance tests.
How many cycles?
We run the entire drivetrain through over 10,000 cycles of hover to cruise mode switching. This proves not just the durability of the K0 clutch, but the precision of the synchronization logic over time, verifying that the engagement accuracy is consistently maintained within that tight plus or minus 2% RPM tolerance.
And you simulate the absolute worst-case scenario for heat management.
We perform extreme thermal testing. We put the entire powertrain, including the battery and the ICE, in an environmental chamber and simulate zero ram air hover conditions in a blistering hot environment, specifically EASA plus 35 degrees C.
So hot day, no airflow, max power.
The worst possible combination. This test pushes the cooling systems to their absolute limits, proving the system does not experience thermal collapse or unacceptable power loss when it needs maximum output.
All this V&V culminates in the final proofs submitted to the regulators to satisfy the means of compliance.
Yes. For the System Safety Assessment, SSA, we deliver the final report with pages and pages of quantitative FTE calculations, mathematically proving that the catastrophic event probability is, in fact, less than 10 to the minus 9.
And for propulsion safety specifically.
To satisfy the detailed propulsion safety SCE-19 requirements, the test data must prove that under any single sensor failure scenario, a scenario we injected ourselves, the resulting thrust fluctuation is strictly under 10% and does not lead to permanent thrust loss. This guarantees the aircraft remains controllable.
This entire arduous process must clear the 4 pillars of acceptance criteria, the final quantitative hurdles the P-13 system has to clear before moving to manned test flight.
These 4 pillars are the final gatekeepers. Pillar 1. The FTA conclusion must be less than or equal to 1 times 10 to the minus 9 per flight hour, period.
No exceptions.
Pillar 2. The FMEA integrity must show 0 catastrophic single failures identified. If one exists, the design must be modified and the process restarts. Pillar 3. Latency. Total fault response delay from detection to protection must be strictly less than 10 milliseconds for high-risk events.
And the last one.
And Pillar 4. Test coverage must be a 100% pass rate for all requirements-based testing, guaranteeing every single validated requirement has been successfully demonstrated. No exceptions. To summarize this immense technical journey, the core message of the P-13 safety case is that we are not relying on just a pile of redundant hardware. We're relying on a complete, systematic MECE engineering practice.
That's the whole process.
The whole process. It begins with aligning with global regulations, proceeds through rigorous architecture design that separates failure paths, quantitative hazard analysis, and culminates in comprehensive integration verification on the Ironbird. This systematic approach achieves the optimal balance between technological leadership offering that crucial range and payload and absolute airworthiness compliance.
That focus on systems engineering is critical. In reviewing the engineering specifications, 3 strategic actions for continuous improvement really stand out. First is the commitment to safety shift left.
Right.
Meaning you must complete the rigorous functional hazard assessment before the architecture is fully frozen. You design the structure around the safety needs, not the other way around.
Which saves immense rework later. Second is the robust, long-term verification of that critical K0 clutch. As the high-risk, high-stress interface, we need to implement accelerated life testing on the Ironbird for thousands of hours beyond the standard mission profile to prove its long-term reliability.
You have to prove it with a significant safety margin.
A very significant margin.
And third, establishing a digital twin-kill platform for seamless compliance evidence. This sounds like future-proofing the certification process itself.
It is. When regulators need to audit compliance, they won't just look at static paper reports. The digital twin allows them to audit the compliance evidence dynamically, injecting failures and verifying results in real time. It builds trust and accelerates future iterations.
Okay.
Precisely. Now, for you, the learner, we've just detailed the extreme lengths required in systems engineering and redundancy to make this complex hybrid machine safe. The integration of thermal and electric power creates unprecedented complexity, but also unprecedented capability, solving that problem of range and reserve energy.
Right.
The key question for the future, which builds directly on this fail-safe architecture, is this. How does this extreme focus on quantitative, deterministic, and fail-safe propulsion architecture fundamentally redefine the pilot's role in future flight operations? If the machine is responsible for millisecond fault detection, isolation, and system reconfiguration, what does the human pilot become responsible for? What decisions are actually left in the cockpit? Something to mull over as AAM transitions from the prototype phase to certified reality.